Hi, we're team number 4 and we're part of BLDG 490 and we'll be presenting our design engineering project. So to begin, we'll be starting with an introduction, followed by the structural design, the envelope design, HVAC, the integrative design, as well as the conclusion to finalize, so you can skip through whichever parts you desire to watch. About the project, it's based on the Bois Co-op in Laval. All BLDG 490 students obtained the architectural plans for it. And the location that we decided on is the same as the current Laval location. But rather than it being a co-op, it's actually going to be designed for senior residents as a condo unit with condo units. Due to there being one structural team member, there's going to be the design for the 6-story wing as well as the 6-story wing also. And the energy consumption goal for the building is 173 kilowatt hours per meter square. And our budget is a total of $10.3 million. So on to the next part, which is the structural design, which I will be presenting. Hi, my name is Tina, and today I'll be discussing the structural design of our project with you. The structural objectives of our project were to have a flat plate design, and this was for aesthetic purposes, as well as to have more ceiling space for the ductwork. Further, it was hoped that the design would be over-designed because it's preferable over having one that's poorly designed and failing when the analysis are performed. And just as a reminder, the condo is a building for senior residents, and there's a 6-story wing as well as a single-story wing with a parking garage. And the architectural plans were provided for Bois, and this is what the design is based on. Oops. The materials used for the building were concrete and steel reinforcements, and the main reason why concrete was used over steel was for its thermal mass benefits. And because it's made out of concrete, the system is a concrete skeleton, so the columns are going to be discussed, as well as the shear walls, the footings, etc. But first, beginning with the structural loads, the dead and superimposed dead loads evidently come from the self-weight of the structure, the HVAC equipment, as well as the envelope partitions and cladding. And the live loads that affected the design were mainly the 4.8 kPa due to the exterior balconies, as well as the corridors because they measured more than 1,200 millimeters. And the ground floor is also 4.8 kPa because of its multiple purposes. And the condo units were 1.9 kPa, and for the parking garage, 2.4 kPa for regular sized vehicles, the standard. In terms of the rain and snow loads, those that are accounted for are the greater among the two, as well as the live load of the roof, which was 1 kPa. But given that the building location is in Laval, it was expected that the snow loads would be higher, and this was the result. And all the snow load equations are presented here, and they were used in the ETABS analyses as well as the SAFE analyses. For the structural loads between wind and seismic, again, a comparison was done between the two, and it was also expected that given Laval is near water, and it's the second most critical in Canada to have earthquakes, the seismic design was critical rather than the wind. And in order to determine this, the static force procedure was compared between the two. And it was actually found that we couldn't use the static force procedure and the dynamic force procedure had to be used. And this was done on ETABS. Just showing this little video here. This was done on ETABS, and the forces that were found was actually used to design the shear walls mainly, but also they were added to the columns afterwards to see if the analyses that were performed doing hand calculations were okay or not. In terms of the design, we'll begin with the columns. The columns that were designed were 3 different column sizes, 550 by 250 millimeters, 600 by 300, as well as 800 by 400. The vertical reinforcement size required is 25 m, and the tie size is 15 m. For the tie spacings, there are 250 millimeters, 300, and 400 millimeters respectively, going from the smallest column to the largest column. And the analyses were performed using S concrete. In terms of the hand calculations, it was required to find the tributary areas. The columns were grouped based on their placements of inside the building or at the corners or as edge columns. So it was a very large procedure, but S concrete was a very easy software to use to make sure that the design was adequate. In terms of the one-way slab design, there were many one-ways, not many, but there were some one-way slabs within the 6-story wing. And it was actually assumed through hand calculations that they would be very thick, and this was a little worrisome. But on SAFE, it was actually found that they could be put at 250 millimeters. But there is a section of level 2, which is the roof of the single-story wing, which has one-way slabs, and these had to be designed as one-way slabs. Their thickness is 550 millimeters, and the reinforcement they required for tension was 70 millimeters spacing of 20 M bars. And for the shrinkage and temperature, 20 M bars at 270 millimeter spacing. It's a little bit difficult to see, but the little bars at the top that are tightly squeezed together is the tension reinforcement, and those above is the temperature reinforcement. And those on the bottom, the ones that are coming out, are the temperature reinforcement as well. The two-way slab design was very tedious because even though it was done and it was completed, a lot of the columns failed, and so drop panels were designed as a precaution just to make sure that if nothing else works, they're designed. But it was actually found that puddling could be used. But even with the puddling, as you can see in the punching shear photo on the right from safe for level 2, this is punching shear after puddling was applied. So shear studs had to be designed. And the shear studs were designed in two ways: one for the puddling area, if you wanted to keep the puddling and have the shear studs included, or to have the 30 MPa concrete strength of the slab and then put shear studs instead. I wasn't able to do a safe analysis including shear studs, so both was done just for the sake of design. So these are the shear studs designs. For the shear walls, there are 3 in the building, and they're shown by the photo on the top right. And the P stands for pier. That's how they were labeled in ETABS. And the analyses, the results from ETABS, as already mentioned, the base shears were used to perform the shear design. And the design was performed in S concrete, and the design was performed in S concrete. And just to make sure that the design in S concrete was similar to the hand calculations done, the shear wall on the bottom is actually panel 1, which is P9, as you can see from the picture. And this was compared to the hand calculations performed. And actually, it's the exact same picture, except there are 2 less vertical bars. So this goes with one of the objectives done, is that it was over-designed using hand calculations rather than under-designed. In terms of the load retaining structure, this is the parking garage walls. For the soil data that was obtained by the geotechnical reports, there was fracturing at around 2.4 meters, which was the bedrock level. And so the deeper you went for the excavation, the stronger the bedrock became. And at a depth of 5.5 meters, it was around 75 it was a higher quality, it was medium quality. And this was sufficient. If designers wanted to go deeper, it would be possible as well, but I didn't want excavation costs to be too costly. And so with the design completed, 15 M bars at 500 millimeter spacing is required for the horizontal reinforcement. Shear reinforcement wasn't needed, but it was designed anyways. And for the vertical reinforcement required is 20 M bars at 400 millimeter spacing. Finally, for the footings, again, according to the geotechnical report, isolated footings and strip footings could be used for the design. And from the safe analysis, the columns didn't experience any punching shear. So that was great. And also the deflection was less than 5 millimeters. It was actually it was 1 or less. And so this was very good. It was nice that the design was over-designed. And if anything in the future, it could be the fact that the slabs are very thick. They're both, for the strip footings and the isolated footings, they were designed as 1.1 meters thick. And if ever it wanted to be changed and reduced, I believe it could have been a possibility, but due to lack of time, more analyses couldn't have been done. So for the isolated footings, they were mainly 2 by 2 meters, but for the columns, especially subjected to the 4.8 kPa towards the middle of the building, they had to be 2.5 meters by 3 meters. And for the strip footings, which were for the shear walls, they're 2 meters in width as well, and 1.1 meters in thickness. Finally, for the cost, this is the cost mainly due to the quality of steel and concrete. It also includes some of the costs for construction and labor, such as barmen needed and setting up the concrete forms. But mainly this all the rebar was calculated, all the steel and all the concrete quantities were calculated. So 211,395 kilograms of steel and 3,347 cubic meters of concrete are needed. Thank you very much. And next, the envelope design team will present their work.
So hello, today myself, Kayleigh, and my colleague Gopika, we will outline the design of the building envelope for our condominium. So since the beginning of the project, there was much emphasis on the performance of the building envelope, highly due to the fact that it is unquestionably the largest visual component of the building and also significantly contributes to the overall performance of the building itself. This is an outline of what we will be talking to you today. We will go over some of the project objectives that were established at the beginning of the project, outline a lot of the design components, along with some of the analysis and a final cost estimation. So to review some of the project objectives that were established preliminarily and that were also thoroughly reviewed throughout the process of the design, these exist in both terms of client requirements and design objectives. They also include consideration mainly of the stakeholders that were most affected by the resulting product, being the occupants of the building, and also the adequacy of the design itself to fulfill the basic fundamental requirements of a general building envelope. Another preliminary design concept was to identify all of the design parameters, the constraints, and analyze through the use of performance indicators. This revolved a lot around the importance of both the regulation and resistance between the indoor and outdoor environments, both in terms of above grade and below grade systems, because the conditions vary significantly. Another important factor that we wanted to consider was that of sustainable development and implement the concept and its presence in as much of our work as possible. The performance indicators were generated through the use of several methods of analysis and then using the data obtained to make any necessary adjustments. And some of this will be discussed further throughout the remainder of this presentation. So to jump into the design, we will start with the above grade exterior walls. For the purpose of this project, the cavity wall assemblies and the air barrier wall assemblies were considered as alternatives for design. And ultimately, the brick veneer steel stud system was chosen, mostly due to the fact that they are historically common and reliable. From the assemblies shown, it can be seen that the layers are typical of this kind of system, including the vapor barrier between the gypsum board and the steel studs. There also is a layer of exterior sheet. There is also a layer of exterior sheathing, rigid insulation, air cavity, and of course the brick veneer. The ClearPath RSI was found to be 6.42, so approximately 59% increase over the NEBC requirement and a 78% increase over that of the Quebec Building Code. What we think is particularly interesting about this design is that we've decided to go ahead with rock wool insulation for both the batt and the rigid insulation. This is a brand that specializes in stone wool manufacturing, and ultimately their products are sourced from stone. So its selection was mainly based on the sustainability in both its use and its production, coupled with its notable fire resistance and acoustic insulation. So I will now pass it on to Gopika, who will discuss the detailing of our roof assembly.
Thank you. So for our roof design, our initial objective, as previously mentioned, was to meet the NEBC standards. In addition to that, we also intended to create a highly durable surface for the heavy loads that a roof is designed to carry. This includes environmental loads and also dead loads from the presence of HVAC equipment. Earlier on in our design, we debated between a cold roof option, and this was explored, but it proved to be ineffective for our given location and climate. Our analysis of its hydrothermal performance using the glazier method demonstrated risk of moisture problems. And so therefore, we didn't analyze this further, and we switched to a warm roof assembly design, typical for our given climate zone. For this design, we chose a single-ply thermoplastic polyolefin membrane. Single-ply membranes intend to reduce complications often associated with built-up roofing systems where they have complications within their multiple layers. As well, TPO is becoming increasingly popular for its strength and durability. We also went with the same rock wool insulation as per the exterior walls, again for its eco-friendly and effective insulating properties. This yielded an overall RSI value of 11.6, which is nearly double the NEBC requirements. This design was further analyzed for its hygrothermal performance through Glazier and Roofy Pro, and both analyses demonstrated effective resistance to moisture penetration. For our fenestration, our objective was to design and select high-level energy performing windows. And this was initially based on ASHRAE standards that outlined triple glazed assemblies with low emissivity coatings as effective for energy performance. Based on this initial design, we selected a manufacturer, namely Cascadia Windows and Doors, to meet this requirement. This manufacturer not only passive house performance standards, meets passive house performance standards, but also has flexible configurations. Based on their MS in material data sheets, we inputted their assembly designs into window and therm approximately, and we yielded a center of glass use factor of 0.783.
So to step into the hygrothermal performance of the above grade system, this was analyzed through the use of both the Glazier method and through the use of Roofy Pro, which was touched upon by Gopika earlier. With regards to the Glazier method, both the above grade walls and the roof assemblies, the warm roof assemblies deemed adequate, and results showed no risk of condensation throughout the assemblies. Also, as previously mentioned, this is the method of analysis that was used to determine the moisture penetration problem that we had occurred with the originally designed cold roof assembly. So regarding the Roofy Pro analysis, the conditions were analyzed and the properties that were also analyzed were the total water content, the relative humidity, and the dew point temperature. The total water content of both assemblies did not surpass 20 kilograms per meter squared, and the relative humidity never reaches 100% within the assembly. However, there was indication of moisture on the exterior surfaces, which is reasonable due to the fact that there is direct contact with the exterior environment. Lastly, the dew point temperature does not exceed the temperature within the assembly, indicating a low risk of condensation throughout. So the overall building envelope transmittance was also analyzed using two equations provided by Morris and Hirschfield in their thermal bridging guide, which is shown on screen. The overall transmittance of the building envelope, including the fenestration assembly, was found to be 0.4426, so approximately an overall RSI of 2.259. For the overall transmittance, including the effects of thermal bridging, the result was found to be U factor of 0.527. These values are unfortunately higher than what we would have liked, but it is important to note that a lot of the data regarding the assemblies was taken from the thermal bridging guide for this specific analysis. And while the data is precise in practice, it is not 100% representative of our designed assemblies. Next, I will briefly touch upon the cost estimate for the overall building envelope. So our preliminary cost estimate was assessed in terms of cost management. It was estimated that the cost of the building envelope would rise to approximately 20% of the overall building cost, which was budgeted at 10.3 million. Ultimately, the building envelope budget was estimated at $2.6 million. Based on data used from RS Means online, the 2011 data, the base material cost and the base labor cost was determined, and then an inflation rate calculator was used to determine the current cost in 2021. This gave us a cost estimate of just under $2 million, and this includes a contingency of 10% of the overall budget.
Hi, I'm Gabriella, and this is Tony, and we'll be discussing the HVAC portion of our building with you today. For our initial design, the building was devised into thermal zones according to the zone type. The zones were described using the NACB and ASHRAE 62.1 guidelines. It should be noted that the zone specifications of the corridors was designed in order for them to be pressurized by supplied air. The recommended airflow of 40 CFM per unit connected to the corridor was used.
And to that extent, if we look carefully at the actual figure that was provided in Gabby's last slide, we would notice that the actual mechanical room is located on the first floor of the building. This being a central location that we're looking after in order to minimize the size of the duct, pipe, and conduit runs, and thus help reduce the power requirements for pumps and fan motors. A minimum of 1% of the building's gross area would need to be provided for the mechanical room. And in this case, the size of it is 78.75 meters squared, which is much greater than the 54.73 required. Now, the reason why we didn't use the rooftop in particular was to help avoid any additional loads that would be applied onto roof already, considering what HVAC equipment would be located there. And in this particular sense, the apartments on the first floor meet the specific size. So we were looking at specifically apartment A102 being the most westward corner apartment of the first floor, allowing us to, in a sense, also isolate the amount of sound that would be coming from this room in particular, only having one directly adjacent neighbor.
Now looking at the heating and cooling loads, these were found by simulating the building in Design Builder. The building was separated into 4 quadrants in order to have a better idea of where actually the building was susceptible to heating gains and losses. We see in the figure that the southeast quadrant experiences the most heating losses, whereas the southwest and the northwest quadrants are experiencing the highest heat gains. Now, taking a look at the system overview, we see that the ventilation is served by a direct outdoor air system, which will provide 100% conditioned air to the zone. The DOAS is paired with a heat recovery in order to recover heat from the return air. We can achieve a higher heat recovery efficiency by using DOAS rather than a common in-suite heat recovery method, since the equipment is larger and has more free space for a larger heat recovery. The DOS is also paired with a demand-controlled ventilation device using CO2 sensors in order to reduce the ventilation when needed. The DOS is served by an electric boiler and a water-cooled chiller in order to condition the outdoor air. An electric boiler was chosen in order to keep the HVAC system completely powered by electricity and in turn by renewable hydropower. This was possible since the boiler only serves the DOS, which does not require a high capacity, which is often the limitation for electric boilers. The water-cooled chiller was paired with a heat exchanger and a cooling tower. The water-cooled chiller was shown to be more efficient than an air-cooled chiller when simulated in Energy Plus. Since the building is located in Quebec, there is an abundance of water, and a water-cooled chiller can be considered an appropriate choice as the cooling system. The zones are conditioned by air source packaged terminal heat pumps that are designed for cold climate with a supplementary electric coil. The packaged terminal heat pumps showed to be 54% more efficient than fan coil units in terms of heating when compared in Energy Plus.
When it came to actually the selection of the DOAS system, we had actually used the data that we had simulated and given it to an actual representative of GreenHEC, as well as putting it into their program that you can find online, being ECAPS, to effectively determine the most suitable model for this entire project, this being the GreenHEC DOAS 150 RVE, RVE being their actual heat recovery system model, being specifically having a heat recovery wheel. Now, to that extent, also, each dwelling unit in the entire complex would have a CO2 sensor, allowing it to provide feedback to the DOAS in order to manage the amount of fresh outdoor air supplied and maintain acceptable levels of CO2 in the space. Now, when it came to actually shafting or the ventilation distribution of the actual system throughout, an attempt was made in order to reduce the amount of ductwork needed throughout the entire building to save on both energy as well as overall just cost. And this design was actually pulling inspiration from the designs of sustainability architect Mick Pierce's environmental award-winning buildings. And these buildings located in Africa and Australia commonly resulted always usually in a 90% natural climate control system, with temperatures inside being around 28 degrees Celsius during the day and 14 degrees Celsius at night, whereas generally the outdoor temperature fluctuates greatly from anywhere 40 degrees Celsius to less than 0 degrees Celsius throughout the entire day. So with particularity, with our project in mind, if you look at specifically the images circled in the figure above, then you'll notice that the supplied air is pushed through the main supply trunk and ducted above to the hollow floors of the zone. This fed air is then released into the zone via perimeter linear floor grills, and as the air is warmed by human activity, it rises to the vaulted ceiling space or plenums, where it is then sucked and returned to the DOS via one of the many return shafts spanning all 6 levels of the residential building. And as a result of taking advantage of the stack effect, apart from ductwork connecting the DOS to the return shafts, no ductwork is actually present for the return of the building's ventilation. With that being in mind, when we talk about the air distribution of the entire system, there's the underfloor air distribution being around 200 meters elevated from the floor itself, being the hollow floors. And then this is actually only applied solely to the dwelling units, as they were the zones that would benefit the most from this instilled natural airflow and circulation. The dwelling units are essentially where the residents would spend the most of their time. And so it only made sense to have the most ideal and best circulation here. In terms of the actual return system, ceiling plenums spaces are found in every zone of the building, barring the mechanical room, which has an open ceiling plan, and they are connected via one of the many running shafts throughout the entire 6 levels of the building, again, as mentioned before. And finally, it is important to note that although this is true, the corridors themselves do not have any return, as we wanted to keep this zone pressurized. Now, with regards to the actual ductwork, the entirety of the ductwork was sized using the McQuay air conditioning duct sizer design tool. And from this, we also applied the values and related aspects that would be present for a duct system, such as itself being a low pressure duct system for this multi-unit residential building. And furthermore, a rectangular ductwork was chosen over round ductwork for the entirety of the system, being for 2 specific reasons. The first one being that they occupy less space, therefore allowing more space in the ceiling plenum for air to circulate. And then the second one being for that they are more common or better for a low pressure system, such as the one that we have here. Now, when it came to equipment selection, similar to the DOAS in terms of equipment selection, representatives and manufacturers for all of the equipment selected were contacted, as well as provided programs for them in order to simulate the best outcome and best model for each one of the equipment selected. This being the electric boiler, the water coil, the water cooled chiller, the heat exchangers, the hydronic pumps, the cooling towers, the PTHP, and the diffusers alike. Anything and everything of the sort was actually contacted through. So this gave us a more of a realistic look on the equipment selection itself.
Pipework is sized using Trend Pipe Designer, where the three hydronic loops were separated into 11 sections. The results showed that 6-inch PVC pipes will be required for all sections. PVC was chosen since it's recyclable and an environmentally friendly product that is light, durable, and cost-effective.
Now, with regards to the actual PTHP model that we had selected, seeing as it is an air-to-air model, this would have to be installed against an exterior wall for each dwelling unit, and as well as every other zone that it would be found in. Now, in particular, every zone, barring certain ones, are actually using only one PTHP having installed inside of them. The other ones being the dining room, corridors, as well as the commercial kitchens. The dining room having 4, the commercial kitchen having 2, and then each corridor of the actual building having 2 as well, each located inside as well.
Now, taking a look at the energy analysis, the building was simulated through Energy Plus in order to evaluate the energy consumptions of the building. We see in the top right graph that the building does consume more energy in heating and pumps than the baseline system. This can be acclimated to the implementation of actual equipment rather than just guidelines that may not always be as plausible than actual equipment is. In the chart below, we see that most of the energy consumption comes from the heating of the building. This is expected for a cold climate building. We follow with the lighting and the interior equipment having the second and third highest energy consumption. The cooling portion notably consumes a low percentage of energy, which illustrates an efficient cooling system, as well as when we see in graph 1, the cooling system only needs to work hard for a span of 3 months. Graph 1 demonstrates the monthly energy consumption of the building as well as its savings. The savings come from the solar wall, which will be further explored in the coming sections of the presentation. As a result, the building consumes 140 kilowatt hours per square meter of electrical energy. This falls comfortably under our goal of the provincial average for multi-unit residential buildings of 173 kilowatt hours per square meter.
Finally, when we look at the actual materials cost, this being for the HVAC equipment, ductwork, and piping, we found that the total cost that we obtained via also contacting the suppliers and manufacturers was roughly around $402,000, being around $73 or $74 per square meter. And finally, with the most recent Hydro-Quebec prices being as of April 1st, 2021, the pricing for an annual energy cost was around estimated to be $4,722,000 or roughly $863 per square meter. And with that, I'm now going to pass it along to the integrative section.
Kayleigh, Gabriella, and I will be discussing the integrative design of our project, which includes the design of a solar wall system. Beginning with the shear wall, there are 60 panels and each panel weighs 40 pounds. This equates a factored load of 20 kilonewtons and a factored moment of 370 kilonewton meters. The visual here shows panel 2, which corresponds to Pier 2. And after performing the analysis on S concrete, it was with the rebar and concrete thickness originally designed for. The additional loadings didn't affect the design, it was still adequate. And so this proves that even with the addition of the panels, it doesn't harm the shear wall design. And in addition to this, there's actually a portion of the shear wall that's missing. So it would be further reinforced. The location of the shear wall with respect to the building is actually very efficient and is very secure, given that the shear wall's purpose is to support the building when it comes to seismic loading. Seismic loading is a very critical load that's applied to the building under a short period of time. So this is, as already mentioned, a very secure location, and it's on the south-facing wall, which makes it very efficient.
So ultimately, the way that we've approached the physical design of the solar wall is that the selected PV panels will be directly attached to the concrete shear wall, and a unitized curtain wall system will be installed above, per se. The framing is also attached to the structure and will not carry any of the flooring or roofing loads of the building. The glazing units that were selected will actually be provided by the same manufacturer that the remainder of the fenestration system that will be provided by Cascadia Windows and Doors. However, for the purpose of this design, a double glazed insulating glass unit system with low E coating on surface 3 will be used. This is mainly due to the fact that the associated solar heat gain coefficient is at its highest, being 0.68, as shown on screen. In terms of the PV panels, this will be a Canadian manufacturer called Canadian Solar. The modules are a monocrystalline silicone with a 19% efficiency, and each cover a surface area of approximately 1.67 meters square in size. From these dimensions, along with the dimensions of the solar wall itself, it was estimated that 60 units will be needed, covering just under 96% of the surface area for the solar wall.
The solar wall spans the entire length of the stairwell and reaches a bit higher than the building of the building's roof in order to connect the supply duct. The thickness of the cavity is optimized for the largest energy savings. A fan with a constant velocity is used to provide preheated air to the DOAS. Temperature-controlled dampers are implemented in order to allow for optimal tempered air. An energy analysis of the solar wall was modeled using MATLAB through a steady-state thermal analysis approximation. A nodal temperature network was used to determine the temperature of the air being supplied to the DOAS. Steady-state heating and humidification was simulated in order to find the energy savings from providing preheated air to the DOAS. The program found that the annual energy savings from the PV panels is 6 kilowatt hours per meter square. The annual energy savings from the supplied preheated air is approximately 14 kilowatt hours per meter square, which totals to an energy savings of 20 kilowatt hours per meter square.
To conclude, the cost of our project is approximately $9.4 million, which is $900,000 under budget, and our energy consumption goal reached 140 kilowatt hours per meter squared, which was below the value that we were expecting. In addition, all of our individual design objectives were met, and this project, as well as this program, gave us a preparedness for real life work in different design categories. Having envelope, HVAC, and structure working together separately, but also referring to one another when certain values were needed, really taught us about how this is to be expected in the workplace. Any structural values that will affect the building in the future will have to be changed. And if the building envelope reduces the amount of heating and cooling needed, the HVAC design can be reduced. And so this really helped a lot. Thank you for watching.